Hello. Okay. Some basic exercise of this fact. Let phi R2S be a ring homomorphism I subset of R, J subset of S be ideals, then what happened? I extension then contraction. It is bigger. I contained in I extension then contraction. Number 2, J contraction extension is smaller. Contraction extension is subset of J. Number 3, I extension equals to extension contraction extension, and J contraction extension contraction equals to J contraction. Okay, you can recall that what is this is I extension, here it is written, and what is J contraction? Phi inverse J, that is J contraction. So these are fact basic. Suppose if I want to prove one, let X belongs to I, then what is I extension? Phi I X, then phi X equals to phi X into 1s, that belongs to I extension. This imply X belongs to phi inverse I extension, that is I extension contraction. This is simple proof. So I subset of I extension contraction. Number 2 is again simple. Let here let Y belongs to J contraction extension. What is J extension? That is J contraction extension equals to phi J contraction S. So there exist x1 x2 xn. Y can be written as summation phi xi si I equals to 1 to n, where xi belongs to J contraction 1 lesser equals to I lesser equals to N. If you have any query and question, then ask me. This implies Y can be written as now what is this? Sorry. Now Xi belongs to J contraction. That means phi xi, what is J contraction? Recall, equals to phi inverse J. That means phi xi belongs to J. That means phi xi si belongs to J. For 1 less equals to I lesser equals to N. For 1 lesser equals to I lesser equals to N. Okay. So summation phi xi si belongs to J. This implies Y belongs to J. Hence, what happened? J contraction extension is subset of J. Okay. Number 3. At first, we note that if I1 subset of I2 subset of R be ideals, and J, I should write here be ideals J1 subset of J2 then I extension subset of I2 extension. Why? Phi I1 is subset of phi I2. This implies phi I1 as subset of phi I2 as I1 extension is subset of I2 extension. Similarly, J1 subset of J2 implies phi inverse J1 is subset of phi inverse J2. That means J1 contraction is subset of J2 contraction. Now we have I subset of I extension contraction. I have just proved here I subset of I extension contraction. Therefore what happened, this imply I extension contraction extension by this result. Next we take, let y belongs to I extension contraction extension. That means y belongs to phi I extension contraction extension. Sorry, what is the extension? That is S. So y can be written as phi xi. Y can be written as, 1 minute, someone message me. Phi xi si I equals to 1 to n. What is a xi? Extension contraction 1 less equals to I less equals to n. So what happened? So xi belongs to I extension contraction. That means that means what is this? This is equals to phi inverse I extension. That means phi xi, I should write here range of I. This implies phi xi I extension. Okay, so phi xi si belongs to I extension. This implies summation, same process, si I extension. This implies y belongs to I extension. So this is one, I should write star. This implies I extension contraction extension is subset of I extension. This I should write double star. From star and double star, we have I extension contraction extension is equals to I extension. Similarly, you can prove that what we can prove, J contraction extension contraction equals to J contraction. Homework, I should write here homework. Okay. Next observation, if P belongs to spec S, then P contraction belongs to spec R. That means if P is a prime, contraction of a prime ideal is prime ideal. If P is a prime ideal, hence phi R2S induces a map phi star spec S to spec R, P goes to P contraction. If you put Jareski topology on spectrum, then you will see that this is continuous also, but I will not discuss it here. I am just telling the fact. Proof. If you have any query, then ask me. Now what is this? Let AB product belongs to P contraction. This implies phi AB belongs to P, phi A, phi B, P. Since P is the prime ideal of S, we have either phi A belongs to P or phi B belongs to P. That is, A belongs to phi inverse P, or phi inverse P means P contraction, B belongs to P phi inverse P, that is contraction. So phi inverse P contraction is a prime ideal. So the prime ideal. Okay. Now question is, or I write here definition. And question, what are the ideals of the quotient ring R mod I? Number 1. Number 2, what is spectrum R mod I? Spectrum R mod I, that means what are the prime ideals of R mod I? Number 3, what is max spectrum R mod I? Now this is the question. So please note that answer. Ideals, my claim is ideals are of the form, or just I write here J mod I what is this x plus I such that belongs to J with I subset of J. Proof, you know that uh, at first it is easy to observe these are ideals that J mod I subset of J are ideals of R mod I. Check. Now if Q subset of R mod I is an ideal if it is an ideal, then what happened? We consider if I should write suppose is an ideal. We consider the map, the canonical map means ring homomorphism R2 R mod I x goes to x plus I. No, that's subjective. And we recall the result if this result if phi is surjective, then phi I equals to phi I into S, hence phi I is an ideal of S. If it is surjective, then phi I is an ideal of S. Okay. Now what is happening here? 0 plus I belongs to Q, because you know that in every ideal 0 is there. This implies pi inverse 0 plus I is subset of pi inverse Q. That is Q contraction. Now what is pi inverse 0 plus? That is kernel pi. That is equals to I. We check that is kernel is I. So I is subset of Q contraction. Let us denote Q contraction by J. So I subset of J. Now what is Q. What is Q? Q equals to pi inverse Q, because pi is surjective. Now pi, what is pi inverse Q? That is Q contraction. That is pi j. What is pi j? X plus j, x plus I, sorry. What is the map? Such that x belongs to j. In my notation, this is j mod I. Therefore, our claim has proved. Number 1. Number 2. Spec R mod I is exactly P mod I, such that I subset of P belongs to spec R. Let Q belongs to spec R mod I. Since Q is an ideal of R mod I, and every ideal of R mod I of the form J mod I, so by problem number 1, we have I subset of J such that Q look like J mod I. Since Q is a prime ideal, this implies spec, sorry, not spec, this implies R mod I quotient Q is an integral domain. This implies R mod I quotient J mod I, that is isomorphic to R mod J, is an integral domain. This implies J belongs to spec R. Now we can write it is as if and only if way. Therefore, our claim has proved. Three. Similarly, just we write it as for maximal ideal, we write it as field, not integral domain. Then similarly we can prove that max spec R mod I equals to M mod I, such that M, I subset of M, and M belongs to and M belongs to max spec R homework. Okay, definition. Let R be a ring. My ring is always uh, my ring is always commutative with 1. R is said to be a local ring if it has only one maximal ideal.
Sir, why you assume R as commutative? The matrix ring is not commutative. So why commutative? We assume unital ring I can understand, but why commutative?
Now my session is only for commutative ring now. After that we can extend this. At first learn commutative ring, then we will go to non-commutative ring or etc. Let R be a ring. R is said to be a local ring if it has only one maximal ideal. So can you give an example of a local ring? Notation. Give me a ring which has only one maximal ideal. This is my notation. That is R, M. That means R is ring and M is the maximal ideal. So can you give me example of local ring?
I'm just assuming. Can we take Z9 and
Z
03 Z9?
Z
The
mod
ring
9
has
Z.
Z9. Yes.
Yes, it is local. And what is the maximal ideal?
Uh, The three orders approve of it. I think that should be a maximal ideal.
No, what are the ideals? I have just said these are ideals. J mod I. So what are the ideals of Z mod 9Z? So are ideals are what is uh, some J that subset of 9Z. Now ideals of Z are AZ form, principal ideal. So I can
Hmm.
write it as AZ. Now this imply 9Z subset of AZ. This imply what? A divide 9, right? Right.
Yes. Yes.
So A option is 1 is
One
whole
three.
ring. This is trivial. A option of A is 3, right? Only, or 9. So ideals are 3Z, 9Z. If you take 1, A equals to 1, then it is Z, it is not proper. And if you take 9Z, it is 0 ideal. 9Z quotient 9Z, that is 0 ideal. So this is one proper ideal. Now Z mod 3Z and 9Z quotient 3Z mod 9Z, what is this? This is isomorphic to Z mod 3Z, which is a field, finite integral domain.
Yeah.
Therefore, this fellow is a maximal ideal. Okay, so your answer is right, but the way you have solved that is
A- Actually, I say Z9, not Z by 9Z. So that's why I face the difficulty.
Z9. What is the difference between this and this?
No, no, there is nothing difference. Just in saying, there is no
Oh.
difference. Just in saying.
Okay, I erase this example. Not erase. I probably keep it. Okay, I just do some here. Okay, what is this? I think I am not. Okay, I keep it. This example of now I am constructing some local ring. Hmm. Observation: if P is prime ideal, then radical of P to the power m of R is actual P. Proof.
So what is the radical? I forgot it.
Okay, this is very important thing. This is the radical. Let I be an ideal of R. Radical of I, root I, that is R belongs to R such that R to the power
Some
n
power of
belongs to R, and we have a fantastic result. The nil radical. If you take I equals to 0, this is called the nil radical. And nil radical
yes,
is
nil
equals
radical.
to the intersection of all prime ideals. Okay, so
Yes.
proof. Note that root p equals to p. What is this? Uh, it is obvious that by definition, where definition? By definition, it is clear that I subset of root I, because r to the power 1 belongs to I, then I subset of root I. If r belongs to I, then r to the power 1 belongs to I. That means r belongs to root I. Therefore, from definition, I subset of root I. So I have to take, so here p subset of root p is obvious. It is true for any ideal. I subset of root I. Okay. Now I have to write another side. Let x belongs to root p. Then what happened? X to the power n belongs to p for some, since p is prime, p is a prime ideal, x belongs to p. Done. Because by definition AB belongs to P implies either A belongs to P or B belongs to P. So root P is subset of P, and P subset of root P is obvious from definition. Hence root P equals to P. Number 1. Number 2 observation: root over I to the power n is equals to I for any ideal root I. Root over I to the power n equals to root I for any ideal I. Let no at first I write this. At first I write this. I subset of j implies root I subset of root j. This is from one line observation. X belongs to root I implies x to the power n belongs to I for some n. This implies x to the power n belongs to j as I subset of j. This implies x belongs to root j. So root I is subset of root j. Number 3 is that root over I to the power n equals to root I for any ideal I. I to the power n is subset of I. This implies root I to the power n is subset of root I. Let x belongs to root I. X to the power r belongs to I. X to the power rn therefore root I is subset of root I to the power n. Hence from this and this, hence root I is equals to root I to the power n. Now from this result we have, if P belongs to specker, this implies root P to the power n equals to root P equals to P. Root P to the power n equals to root P, and root P equals to P from 1. So we have proved this. You know that every prime ideal is a maximal ideal. Sorry, every maximal ideal is a prime ideal. Sorry, because if M is a maximal ideal, then R mod M is a field. Every field is an integral domain. Therefore, R M is a prime ideal. So max spec R is subset of spec R. Okay. Let construction let R be a ring and you know that if R is a commutative ring, then max spec R is non-empty. This any commutative ring with identity, it has a maximal ideal in my setup, and M belongs to max spec R. Then for any R greater than equals to 1, spectrum R mod M to the power R is M mod M to the power R. Hence max spec একটাই প্রাইম আইডিয়াল আছে, তাহলে সেটাই ম্যাক্সিমাল আইডিয়াল হতে হবে। It has only one prime ideal. You know that max spec R is subset of spec R, and max spec R is non-empty. Therefore, max spec R is that singleton set. In this example, I will prove it, but in this example, this is Z and you have 3Z is the maximal ideal in Z. 3Z is the maximal ideal in Z because Z mod 3Z is a finite integral domain, is a field. Now you take 3 square, so in it is the general result M to the power R. There is 3Z mod 9Z, 3Z mod 9Z, and here it is this R mod M to the power is M mod M to the power. Okay, proof. You know that what is the spectrum of R mod I? spectrum of R mod I is P mod I, P mod I, where I subset of P and P belongs to specker. So let spec R mod m to the power r is P mod m to the power r such that m to the power r is subset of P and P belongs to specker by previous problem. Now m to the power r subset of P, take radicals and use 2, this root over m to the power r is subset of root P. Now m is maximal ideal, therefore m to the power r is m, and P is prime ideal, therefore root P is P. Because both are prime ideals, maximal ideals also prime ideal, so using this result. Okay, this simply m equals to P since m is maximal ideal. Max specker. Therefore spectrum R mod m to the power r is exactly that is m equals to P, so m mod m to the power r. Hence max spec R mod m to the power r is also m mod m to the power r, and the ring R mod m to the power r is local. So we have constructed an example of local ring. Another important things is localization. We'll do it later. Now tell me a ring which has 5 maximal ideal, or you take 7 maximal ideal, whatever you take. Construct a ring which has 5 maximal ideals. Can you construct? And next question is another question. Let n belongs to Z and n equals to prime factorization p1 to the power alpha 1 dot dot pr to the power alpha r. Find nil radical of Z mod or nil Z mod nz. Okay, what is nil? Nil Z mod nz means nil radical of this. That means in my previous notation it is root 0. What is root 0 of this ring? Okay, I write I root over 0 plus nz. What is this? Z mod NZ. So this is question. What is this? So I will stop this class by giving a hint. So use this. Use this result. Nil radical actually prime ideals, intersection of all prime ideals. Now, what are then question is, what are the prime ideals of this fellow? What are the prime ideal of this Z mod NZ? If n has the prime factorization, this. So, finding this, you will use this result. Spectrum of R mod I is P mod I subset of P sub belongs to spec R. Using this and find all prime ideals of uh, Z mod NZ, then find nil radical. Okay. So the I will start this class from next day from here. Okay. If you have any query, then ask me. Any question? Okay, then if you have no question, then I'll stop here today. Thank you. I'm leaving.